If you work in metal additive manufacturing, you already know this. Powder is expensive. And we recycle it because we have to. But the real story is far more complex. Every time that powder passes through a laser powder bed fusion machine, it changes, physically, chemically, and mechanically. And those changes can ultimately make or break the performance of the parts we print. So today we're going to walk through current work on the topic and look at how industry is approaching powder recycling in real laser powder bed fusion workflows. Together, we'll look at how powder recycling truly affects powder characteristics and what that means for the mechanical integrity of the components we rely on in engineering and industry. Let's begin with why this conversation matters so much. In LPBF, powder isn't just a consumable, it's a major economic driver. Powder alone can represent up to a third of the total cost of a part. And after a build, more than half of that powder is still unused. For most organizations, recycling isn't optional. It's the only practical way to maintain profitability and sustainability. But here's the challenge. Each time powder cycles through the machine, it's exposed to heat, oxygen, spatter, vapor, and mechanical handling. And all these interactions begin to degrade the powder. This degradation slowly affects powder bed density, melt pool stability, porosity formation, and eventually fatigue life, especially in parts that operate under cyclic or safety-critical conditions. A key takeaway from research is that powder reuse isn't a simple yes or no decision. Instead, it's an evolving materials degradation process, one that requires thoughtful control. Now that we understand the stakes, let's look at what actually happens to the powder inside the machine. When the laser hits the powder bed, particles near the melt pool are violently expelled. This creates spatter. Particles that are much larger than the original powder, often irregular and usually coated in oxide. Many of these spatters fall right back into the powder bed, slowly contaminating the feedstock. Meanwhile, the intense heat also generates metallic vapor, which cools and resolidifies as ultrafine condensate. These condensate particles, rich in oxides, settle across the bed and dramatically alter how the powder flows, how it absorbs laser energy, and even its thermal conductivity. As the build progresses, oxidation increases, especially in alloys like titanium. Oxygen-rich spatters and condensate shift the powder's chemical composition, which affects everything from melt pool behavior to final mechanical properties. And speaking of melt pools, recycled powder fundamentally alters melt pool stability. Changes in surface chemistry and particle morphology influence Marangoni flow, recoil pressure, and even the width of the denudation zone around each track. The melt pools become deeper but more erratic, and erratic melt pools mean one thing: more porosity, more variability, and a greater risk of defects. With that picture in mind, let's explore how the powder itself evolves over repeated cycles. One of the most consistent observations in the literature is that particle size distribution shifts toward larger sizes as powder is reused. This happens because spatters coalesce. Fine particles are often removed during sieving, and collisions inside the chamber produce fused or elongated agglomerates. Even this single shift can dramatically change powder flow behavior and powder bed density. But the story doesn't end there. Morphology also degrades over time. Instead of clean spherical particles, the ideal shape for LPBF, we begin to see elongated particles, broken fragments, fused satellites, and a host of irregular heat-affected debris. Morphology, more than any other property, has a strong influence on how tightly powder can pack in a layer. This brings us to flowability, which is one of the most controversial aspects of powder reuse. Some studies report better flowability with reuse, others report worse. The contradiction arises because flowability depends on two things simultaneously: the size of the particles and their sphericity. Larger particles may flow better, but less spherical particles flow worse. And the outcome also depends heavily on which flowability test you use: Hall funnel, Carney funnel, RPA, or the Hausner ratio, each of which tells a slightly different story. Ultimately, powder bed density is one of the most critical metrics. Recycled powders often reduce PBD because irregular particles don't pack efficiently. Large spatters interfere with smooth spreading, and the recoater can create local segregation across the bed. Lower PBD means more porosity, and more porosity means weaker fatigue performance. Now let's see how all of these powder level changes translate into actual part performance. When it comes to tensile properties, the impact of powder recycling is surprisingly modest during early reuse cycles. Tensile strength and elongation remain reasonably stable, with only minor reductions that can usually be traced to slightly increased porosity, chemistry drift, or subtle microstructural changes. Fatigue properties, however, tell a very different story. This is where powder reuse becomes a critical concern. Recycled powder increases pore size, raises the likelihood of lack of fusion defects, and introduces greater scatter in fatigue life. For components used in aerospace, medical implants, or any application involving cyclic loading, even small increases in defect populations can compromise safety margins. That's why high reuse ratios must be approached with caution in fatigue-critical environments. Now, you may have noticed that different sources often report different outcomes. Let's talk about why. Various reviews identify 6 major reasons for conflicting results across the literature. First, researchers use different recycling strategies. Some reuse powder exclusively, while others mix in fresh powder through a top-up approach. Second, sieve sizes differ widely, meaning some studies remove heat-affected particles, while others inadvertently leave them in. Third, oxygen exposure varies from machine to machine and from one facility to another. Fourth, the effect of oxidation depends heavily on the material itself. IN718 tends to be chemically stable, while titanium alloys are extremely sensitive to oxygen pickup. Fifth, build geometry affects how much spatter is generated. Lattice structures, for example, tend to degrade powder more aggressively. And finally, even the spatial position inside the build chamber, north versus south, front versus back, can influence both powder degradation and mechanical properties. Understanding these variables is crucial for designing a recycling protocol that is predictable and repeatable. So what does effective powder management actually look like? According to the review, the most reliable strategies start with controlled top-up blending, adding 20 to 30% virgin powder at each cycle to counteract degradation. Keeping oxygen levels tightly controlled inside the build chamber is equally important, especially for oxygen-sensitive alloys. High-frequency ultrasonic sieving helps break apart agglomerates and remove oversized particulates, while routine monitoring of particle size distribution and morphology ensures that degradation doesn't go unnoticed. Moisture-controlled storage, along with occasional vacuum baking, prevents humidity-induced clumping. And finally, real-time spatter monitoring is emerging as a powerful tool for estimating contamination rates and predicting when powder needs to be refreshed. The overarching message from the review is clear. Powder recycling is absolutely feasible and increasingly essential, but only when managed with discipline and precision. So what's the big picture? Powder recycling isn't inherently good or bad. It's a materials evolution process, one that must be measured, controlled, and understood. If we manage oxygen levels, maintain effective sieving, track PSD shifts, and pay attention to flowability and powder bed density, then recycled powder can be used sustainably, safely, and without compromising part performance. And that's the real story behind powder recycling in LPBF. Not a simple yes or no decision, but a sophisticated balancing act that combines materials, science, machine control, and process discipline. If you found this breakdown useful, support the channel by subscribing for more practical insights into metal additive manufacturing. Thanks!